Alrighty. So we are all set up here. Excellent. So let me scroll to where we are currently at. All right. Okay. My first question is: did anyone try to use River Spider? Try to get it set up when you're home? Okay. No. Okay. So did it work? Okay. You got it to work the way that I demonstrated in class. Decompress. Yeah, it depends on the speed of the drive. Yeah, so with certain drives, it work a lot faster. If you are to use like an external SSD, it's going to go a lot faster. But a thumb drive is going to be really slow because a thumb drive, they only give you the burst speed of reading or writing, which means it's not meant for sustained reading or writing of many, many tiny little files, which is what that involved. Oh, so you're decompressing to your own SSD on the computer itself. Okay, well, it can potentially happen while your system is also updating itself. Then it's already using a lot of input output, so the entire bandwidth of file input output was already being used for updating, so your operating system. So that can potentially cause the problem, because if you add additional file input output operations when it's already busy, it would just make things not just linearly bad. It's actually super linear, which means it is worse than separating the two jobs and do one independently. Gotcha. Okay, so you probably are running into that exact problem. Is having two tasks that are both I/O bound or file I/O bound, and yep. Okay. Well, I'm glad we can explain that. um, all right. So if you have not had a chance to make use of or set up River Spider, I would strongly advise you to get it done as soon as possible. Oh, I guess the pen. Stop that thing. The problem with that pen is it's too long. So center of gravity is it's outside of the little notch, so it falls out pretty easily. Now I can fix it by just cutting the pen into the height or the length that I need, but that would be destroying your school property, and that may not bode well either. And then the next question is,
This might be a little messy.
yes. And they will question, what kind of instrument did I use to cut it, and why do you have that instrument in your pocket? So I don't want to have to answer those questions. I suppose if we were to slam that door really, really hard, we can use the door as the cutting instrument. Hmm. I'll explore that option. Alrighty. So where we are currently at is we are done with stack operations, which was what the previous lab was about. The interesting thing was yesterday I had to take time off because of the interviews and also a stomach flu at the same time. Um, yeah, that wasn't pleasant. Um, but anyway, the Monday Wednesday class, basically did the same lab that we did on Tuesday, and I found at least two people in that class using the infinite monkey approach. Basically like 8 attempts, and then the last attempt only took a minute or so. Um, that is not the intent of the labs. The labs are intended to have you to kind of think about, how to answer the question and try to answer the question correctly the first time. The unlimited attempts is intended for people to go back and go like, okay, I don't remember the entire thing. I want to do it again. Okay, but every time a person is doing it, I was expecting people to kind of like, okay, let me do this with a fresh mind and not to, just to get the points, but I want to, understand the material embedded into the lab. So part of the instruction of this class is in the module, okay, that you have been reading, but the other part is embedded into the lab activities themselves. So you'll kind of keep that in mind because you might need to redo a lab several times just to get all the instructions embedded into the labs, such as the one for today is one of these examples. So the one that we're going to talk about today, or the lab that you need to do, is called params and return value. So I use abbreviations here. Params is parameters, and then ret is return, and then we are basically talking about the return value of functions. So for that, we need to talk about caller-callee agreement. So this is one of the most important topics from here on, is how does the caller and the callee, the function being called, talk to each other. So we have already talked about a little bit of this because when we talk about the return address, how the return address is pushed on the stack and how it is popped by the function that is ready to return, that is part of the agreement. But the agreement goes kind of a little bit beyond that. So what we'll do is kind of go through the agreement between the caller and the callee. So first of all, do we have any questions about what I am referring to as the caller and what I'm referring to as the callee? Do we need an example to illustrate what that means, what each term means? Okay, I see some nods. Does that mean that you want me to go through an example or that you already understood the concepts? Okay, which one? Example. Okay, very good. All right. So we're going to go through an example. There are many ways to do this. So I am going to just write a program. Okay, let me see if that is still here. I don't think it's here already. So we'll just write a new program. We have f being a useless function. But to illustrate the concept of who's the caller and the callee, this is not a problem. Okay, remember this program? I sure hope so because we talked about this last in the previous class. So in this case, from the context of this line, okay, on line 7, f is the callee. It is the function being called. Now, many times I would also refer to a function as a subroutine. So in this class, they mean exactly the same thing. Okay, because a subroutine is how the concept was introduced when I went through college. And then, of course, when C came along, a function or a subroutine is called a function. So function, subroutine, they all mean exactly the same thing. Okay, for someone with a Pascal background, it is also called a procedure. Okay, so procedure, a function, and a subroutine, they all mean basically the same thing. Is that okay so far? All right, so if you can memorize all of these equivalent terms from our perspective, great. If you think you might need to jot down, like, okay, these terms all mean the same thing in this class, you might want to write it down. So from the context of line 7, main is the caller, and then F is the callee. So are we okay currently with the terms who is a caller and who's the callee? Okay, so it's always seen from the perspective of what I would call a function invocation, so or calling a function. All right, so I'm gonna go back to the main slide here. All right, so on the caller side, okay, this is the agreement. If there are arguments, the arguments are pushed in reverse order. On TTP, arguments are pushed contiguously with no gap between them. You basically don't have to worry about this unless you already know how a GCC compiles code. Since we have not really talked about how GCC compiled code yet, that means what contiguously means in this case is not relevant to our discussion. So all you need to know is the arguments are pushed in the reverse order. The first argument is pushed last. This implies the last argument has the highest address because it was pushed first. The return address is pushed after all the arguments, and then we jump to the entry point of the callee. So we have talked about these 2 points exactly on Tuesday. So on Tuesday, we actually illustrated how we can push the return address and then use a JMPI to continue execution at the entry point of the callee or the function that we are calling. Okay, is that okay? Okay, does everybody kind of associate these two lines or these 2 points with what we did on Tuesday? Okay, all right. So the callee should return to the instruction right after the JMPI instruction, and that's how we set up the return label. Okay, you'll remember the really long label name. Okay, so that's what the return address is what the label is representing. If the callee returns a scalar value, the return value is assumed to be in register A. Okay, so now we have a new concept here. What is a scalar value? So if you are reading this, okay, what would you do when you look at this and go like, I'm not really sure what is a scalar return value? What would you do?
Look up the definition of it.
Yep, look it up. Okay, so we can do the same thing here. Okay, so I just want to illustrate, what resources are usually, available at your fingertips. So you just look up, what is in C, what is a scalar return value. Okay, so the first one is Stack Overflow. I read Stack Overflow answers too, but typically it is usually not a very good um, uh, it's not a reliable way to find an answer, because there are people who might answer the question incorrectly. The other thing is you can also just look at the upvotes of the answers. So if one upvote, one answer has a really good, like 9 is not bad, okay? So this is not bad. So it says arithmetic types and pointer types are collectively called scalar types. Okay, so does this answer the question? It follows up with the second part, which is arrays and structures are collectively called aggregate, which is non-scalar types. So are we okay with this clarification? Okay, I'll give you an example. Signed int. Is it a scalar or not? It is. Okay, very good. What about in regular C++? What about double? Is double a scalar type? It is. Very good. So the only ones that are not a scalar type are structures. So if you're returning an entire structure, it is not of scalar type. But what if you're returning a pointer to a structure? Would that be of scalar type? Yes, it would be of scalar type. So any pointer is a scalar type. Any integer is a scalar type, regardless of whether it is signed or unsigned. So the only problem with this particular approach is, okay, from the syntax perspective, okay, so let me save this one and I'll go make another program here, return array.c. Okay, this is a really, really bad example, but I'm going to use it anyway. So if I have a function and, okay, I can use a global array, which then makes it not so bad. So I have a global array, which is int array a bracket 5. Okay, it doesn't matter how big it is. So now I have to specify return a. So now the question is on line 5, am I returning a scalar or am I returning a aggregate? So most people would think it is an aggregate, okay, but it is not, okay, because what is this? This is not going to compile because I have to specify the return type of f. So what return type do you think f should be? Hmm? Well, we'll see. Okay, so this is something that I want you guys to see as well, is how do you confirm a concept is correct or not? How do you confirm the understanding of a concept is correct or not? So we first guess, okay, the return type of f should be an int. Okay, so we'll give it a try. GCC-C, which is just compiling without linking, so that we are not we're not concerned about running this program. We just want to check whether it is syntactically and semantically correct or not. It complains and go like returning int star from function with a return type int makes integer from pointer without a cast. So this is already telling us what the answer should be. It is telling us the answer should be this. Okay. Now, are we really sure about this? Okay, let's double check. Let's compile again. No error this time. So the problem with this approach, or the problem with understanding why this program needs to be like this, is because there's no way in C, regular C, to return an array. You just cannot. Whenever you put an array type as a return value, it is always referring to the address of the array. Is that okay? Now, with structures, it's different. Okay, so if I were to make a structure here, okay, so I'm going to say struct um, x is an integer, y is an unsigned. Oh, okay. Int x uh, unsigned y, and I make a variable. This is not a named structure, so the structure is unnamed, but I make a variable called s, okay, for structure. So if I were to return s in this case, it would be returning a structure. Now, how do we know? Oh, I cannot make it unnamed because I have to, otherwise I cannot reference the type that I'm returning. So I have to give the structure name. We'll call it x here. So in regular C, you have to say struct x. So now we're returning a structure. So let's double check whether the compiler agrees. It does not agree because I forgot a semicolon. So this is just a syntax error. It's not a conceptual problem. Okay, so let's do it one more time. It doesn't have a problem. But in this particular example, we are returning an aggregate because we are returning a type that is a structure. Is that okay? So this is an aggregate, which we don't deal with in CISP 310. So I'm not going to teach you guys how to return an aggregate type in the code that we are going to talk about. But we will talk about the case when we return a pointer to a structure. So now we are returning the address of a structure, which means the return type is not a structure, but it is a pointer to a structure. A pointer to anything is a scalar. Okay, so we'll double check and make sure that the compiler agrees with this, and it does. Is that okay? All right, so even though in the notes here, sometimes I just say, oh, it's a scalar return type. If you don't understand exactly what the word scalar means in this context, it is important to find that out. You can find it out by contacting me. Okay, you can go like tech. I'm not really sure what a scalar return type is, and I will basically just lead you through this whole exercise to find out exactly what it is. But it should be one of the concepts introduced in C++ in your previous class, in CISP 360. Is that okay? All right. All right. So in this case, since we are only going to deal with scalar types, the return value is going to be in register A. Okay. The values of registers A, B, and C are not assumed to be preserved. In other words, before you call a function, you might have some special value in register B and register C that you go like, after the function returns, I have some use for these particular values later on. Well, as soon as you call a function, all bets are off. Okay, registers A, B, and C do not need to be preserved by the function that you're calling. So in your mind, you have to basically make the assumption that all registers are going to be changed by the time the function returns to you. Is that concept okay? All right. If there are arguments, the caller has the responsibility to clean up the stack space used by the arguments, if there are any. So from the callee's side, we are only going to talk about a few things, which are the stack pointer, pointing to the return address, and parameters that are pushed on the stack. So if there are parameters, the first parameter starts at the address immediately after that of the return address, and the last parameter also has the highest address. So this part is emphasized twice. It was mentioned here once, and it was mentioned here again in the callers, on the caller's side. And I need to find out where I put it. This implies the last argument has the highest address. So that point was emphasized twice. In the callee's code, additional stack space may be utilized because you have local variables and you might be calling some other functions. So that kind of goes without saying. At the exit point of the callee, if the callee has a scalar return value, use register A to store the return value. So this statement is basically saying the same statement as this one over here. So that's why it is called an agreement. It is a handoff. Okay, when the function is ready to return and it has a scalar return value, it will basically put the scalar return value in register A. By the time controls get back to the caller, then the caller goes like, "Where's my return value?" Oh, right. The agreement says it should be in register A. So it will look at register A for the return value. Is that okay so far? All right. So now that we understand these points, I'll leave this slide open. Okay, and then what we'll do is we're going to take a look at a few examples. So the first example that we're going to look at is called 5.c, because that's all it's going to do. So in C++, okay, or regular C, I'm going to pound include standard integer.h, which allows me to use these particular types because I want to emphasize that whatever the return value is an 8-bit unsigned integer. Okay, because the TTP-ASM has a natural size of only 8-bit wide integers, so I want to match that. So I call this function f5, and it does not take any parameters, and all it wants to do is to return a constant of 5. Is that okay? Now, would you call this a relatively useless function? I would. But from the perspective of what I want to demonstrate, it is actually useful. So now I'm going to do a split because I want to show the assembly code, with the window below this. So I'll call this one 5.ttp-asm. So the entry point of 5 is simply known as 5 as a label. In other words, what we do is we convert the name of a function into simply a label so that we know, where is the entry point of a function. Is that okay? All right. So now we go like, okay, all we have to do is to specify a return value of 5, which is an unsigned 8-bit integer. Is that a scalar or not? It is a scalar. Okay, so we have to put it into register A. Very good. And which instructions should I use if I have a particular value to put into a certain register? LDI. Very good. So LDI A with, in this case, 5. So this would accomplish one of the jobs of line 5 of the C code, because return 5 actually has two jobs to do. One job is to specify a return value of 5, and the second job is to actually return to the caller. So now I have to finish the whole thing, which is to return to the caller. Um, how do I return to the caller? I don't even have the caller code here. This is only about the function being called. So how do I return to the caller based on what we saw earlier, which is the caller-callee agreement? Where do I find the return address? On the stack. And where on the stack? It should be the last thing that got pushed on the stack, which means the stack pointer should be pointing at the return address right now. Okay, so that means I need to do a pop, right? Pop the return address into another register. So I can only pop things into one of the 4 registers, of which 2 I cannot use anymore. Which 2 can't I use right now at this point? Register A, because register A serves a special purpose of the return value, and which is the other one? Register D, because register D is the stack pointer. So those 2 registers I cannot touch anymore. But fortunately, I have 2 more to choose from. I got register B or register C. Which one you choose is entirely up to you. Okay, you can use either one at this point. So I'm going to pick register B. And then we have to continue execution where register B points to. All right, so those are the things that I need to do. The question now is, how do I do that? So I'm going to go through the detailed step-by-step example here. when you pop something in C code, it is copying whatever the stack pointer is pointing to the destination. So in this case, it would be B is getting whatever the stack pointer is pointing to. And then the next item is to deallocate the location that the stack pointer is pointing to. But deallocation in this case is SP. Are we incrementing or decrementing? We are incrementing. Okay, so it is SP plus plus. Okay, so now we know that this is what we need to do if I were to specify the operation in C code. So how do we specify this in assembly code? There's only one instruction that can copy a location in RAM pointed to by one of the registers to a register. And which instruction would that be? LD. It's LD. Very good. So we use an LD, B, and then SP. We go like, wait, the editor knows there's something wrong here. What is wrong in this code? There's no SP. Okay, SP is not a real register. Instead of SP, what do we do? Yep, because the agreement is to use register D as our stack pointer. Okay, what about this one? We have to do an increment of the stack pointer. Which instruction should we use? INC for increment, and which register am I incrementing? Register D, very good. Okay, so this is more or less a reinforcement of what we talked about on Tuesday. Okay, which means, it is important to review those concepts on Tuesday before coming today into this lecture, because if I did not re-mention these points, you should still be able to remember, oh, okay, I remember what those are, okay? You only have to recognize, okay, because I'm not going to test you guys on memorization, which means in the next exam as well as the final exam, it is still open book and open notes like in the first exam. You can bring anything you want that is on paper. It can be handwritten, it can be printed, and you guys can study together, okay, and go like, okay, we all agree that these are the things that we want to bring to the exam. That's fine with me, okay? Study together, come up with a list of things that you think are important together, okay? So now, how do I continue execution of where the register B is pointing to? That was the one instruction that was added or introduced on Tuesday. Well, that sounds like some kind of a jump, right? JMP, just B, without the L, without the I, excuse me. Because with the I, you're using an immediate value to specify where you go to. An immediate value is a constant, which means you can only end up at the very same place every time you execute line 9 in this assembly code. But where we need to return to depends on what is on the stack, which means it is not a constant. JMPD allows you to basically copy register B to the program counter. The program counter is tracking where we should fetch the next opcode, and by changing the program counter, you alter the path of execution. So are we still doing okay so far with that? So ultimately, this relates to the first phase of the instruction execution cycle, because the first phase of instruction execution cycle is what? It's called fetch. Very good. And fetch involves going to where the program counter points to in RAM, grab that byte, and putting that into the instruction register to be decoded later on. So that's why, by changing the program counter, you are altering the path of execution. In this case, we're changing the path of execution so that we can continue with whatever the caller is pushed on the stack earlier as the return address. So is that okay? Is everybody understanding 5 implemented in TTP ASM at this point? So we're kind of good here. Okay, all right. So now we're gonna go, okay, if 5 is easy like this, we'll implement 7. Okay. And here is 7. And it is to return 7 here. And we probably go like, oh, that's easy, right? Because it really is. Okay, so 7, as the word 7 spelled out, is just LDIA7. And then we do a LD, well, this time we can choose D, a C, increment D, JMPC. Okay, that's how 7 is going to be implemented. All right. So now we're going to look into something that's a little bit more complex. Okay, so now we're going to look into a function that's called sum, and it takes two 8-bit unsigned integer. I call this one x, un8 underscore ty, and all it wants to return is x plus y. Okay, so this one, I'm gonna, I will explain this from the perspective of the caller first, because once I explain it from the caller's perspective, it makes it a little bit easier to see it from the perspective of the callee. Okay, so I'm gonna go here, and I'll have main function here. Main is, at this point of this class, I'm just gonna say that main ends with a halt instruction, because there's nothing to do when main is all done. Is that okay? All right. So main is going to be the caller, and I need main to call some with, we'll just say, some constants here. We'll say, 2 and 6 as the argument. In other words, we are just calling some with 2, 6 as its parameters, and do absolutely nothing with the return value, at least for the time being. Okay. So now the question is, how do we do this? Have we talked about conceptually how this should be done in today's lecture? Does the caller-callee agreement cover this? Okay, so you guys can have the caller-callee agreement open in front of you using your own browser. So what is the agreement when I have arguments in a function invocation? What is the convention? What is the agreement? So we have a bunch of stuff to push. So I'm going to guess the things that we have to push includes the return address, the 2, and the 6. The question is, in which order should I push those things? Reverse order of the arguments, okay? So then the next question is, I got a bunch of parameter arguments, but I also have the return address. So between the arguments and the return address, which one should I push first? Arguments first. Okay, very good. So that means the first thing we need to push is what? Yep, so we have to push 6 first, then we push the 2, and then we push the return address. So from here on, I'm just going to use RETADDR to denote return address, so I don't have to type a whole bunch of stuff. Okay. Okay. Do we know how to push something on the stack? Okay. So we want to push 6 first. So we need to put it into a register first. So we put it into, at this point, registers A, B, or C can be used because register A has no special meaning at this point. So I can use register A, decrement D, and then STDA. So that would push the 6, and then we need to push the 2. Kind of the same deal. Decrement D again, STDA. And then we have to push the return address. But to push the return address, I have to know where the return address is first. Okay? So, well, there are 2 ways to look at this. The first way to look at this is simply to say, okay, we have a return address from add, from sum, and just leave it undefined. Okay, just leave it undefined, and then we just go through the whole motion of pushing first, STDA, and then the JMPI to the function. Okay, this is how we usually do things. So according to the caller-callee agreement, where should I put the label defining the point of return? Hmm? So, sorry?
You see the return value?
No, not the return value, the return address, where the function should return to.
Right after the jump instruction.
Yep, yep, exactly. Okay, so it's part of the agreement. Okay, because from the caller's side, the return address is the address of the instruction right after the JMP to the callee, which is the JMPI sum instruction. So that means, from the code perspective, the label should go here. So return address from sum should be defined here. Are we doing okay so far? Okay. Now, if anyone is thinking, reading this thing here is almost like reading a legal document, like, when you're signing up for a apartment rental, there's like a 6-page, legal document that you have to kind of dig through, and then they just want you to sign at the very bottom of that. That's kind of what it is, because a rental agreement is an agreement. Okay. This is also an agreement between the caller and the callee. Why is it important to have these agreements? Because without these agreements, then people can choose to do whatever they want. I want to push the arguments in exactly the opposite order. Well, that's not going to work if the function is expecting the opposite. Okay, so that's why these agreements are important. Between the caller and the callee, they have to agree on how the stack is being used. Are we good? Are we okay so far with this? Okay. So now we go back to the code here and go like, okay, fine. Let's try to assemble this program. But before we do that, we have to kind of finish up the program. At the very beginning, I always want to no op because I intend to use Reefer Spider, so I don't have to go through the long process of doing it. Now, you guys are more than welcome to use the long process, but I don't want to use it if I don't have to. Okay, so we use a no op, and then we quote unquote initialize the stack pointer, which is not necessary. Okay, it's not necessary because when the processor starts running, all registers are reset to 0 to begin with. So this LDID0 is really not needed, but I will put it here anyway. And then we just do a regular jump to main because the reason why I have 5 and 7 defined here is simply to preserve the same order as function definition in the C code. So now we go like, okay, so let's see whether this works or not. I can tell you it's not going to work, but it is good to show you why something is not working and how to debug it. Okay, so now I will go to Documents, CISP 310, Reaper Spider, submit um, where the code is located. So you can do the same thing if you're using Reaper Spider either on a Mac or on a PC. You can basically put your actual code somewhere else as long as you can specify where it is supposed to go to find it. Using Sigwin makes things a little bit more tricky, so it may not be a good idea. If you're on a Mac, it's actually pretty much the same thing. So how did I call that? I think I called that 5. Yep. So 5.ttpasm. Press the Enter key. So this will go through all the things that otherwise I have to do manually. And it says, uh-oh, the source file did not assemble correctly. So what should I do now? Okay, I'll offer you 2 options. One option is to go to the source code and stare at the source code. And then the second option is to go to the assembler and say, what's wrong with this? I think the second option sounds easier, right? So we go to the assembler, okay, which I think is this one. Yes. And then we go to the source tab. So if there are any errors, it's going to be reported in column B of the source tab. Okay, so that's how you debug your program from the syntax perspective. And we scroll down, we go like, oh, okay, we have an unresolved reference of sum. In other words, sum is referenced by this particular JMPI instruction, but as a label, sum was never defined in this entire program. Go like, wow, I forgot to do that. Okay. So now we switch back to the source code. Now you can do the same thing if you want to do it this way. You basically don't do any editing in the spreadsheet because that's actually really difficult. If you go back to the spreadsheet here and you say, I just want to insert a new row, it's going to break the assembler. So it's not that's not a good way to do it. So I would just do all the editing in on the other side and not touch the spreadsheet at all. So over here, I can now go back to the original file, which I actually have already opened on the other side, I think. Let me see. Yep, I still have it open here. So now I can go back here and go like, okay, let's go ahead and define sum. But I don't want to do anything yet. So in other words, I am step by step trying to show you guys, how to understand all this material. In other words, what can I expect to be on the stack at the entry point of sum, according to the caller-callee agreement? Is that okay? Because what should I expect? I should expect 6, 2, and the return address to be pushed on the stack. But in what order? Who is where exactly in RAM? Well, I think I have a pretty good idea. Okay, so location FF should have the second argument, location FE should have the first argument, and then location FD should have the return address. Okay, but I can say this all day long, but it doesn't beat having to actually running this and see what happens when we run it. Is that okay? So that's exactly what we'll do. I have to remember to save the file first because if I don't exit the editor, sometimes I forget to do that. And we'll go ahead and reassemble the program and let it run. There we go. So this time it ran correctly. Okay, but it ran. We don't know whether it's correctly or not. And the trace is already uploaded, and it tells us that we should go to the analysis sheet to look at the trace of the program. So this is the trace. Line 1 is a no op. Okay, it doesn't do a single thing. In other words, it doesn't write to RAM. It doesn't change any of the registers. It did not change any of the flags. To be expected. Okay, nothing special about this one. Initializing the stack pointer to 0. Okay, well, that's initialized. JMPI to main. So that means we continue execution at location 10, which is where main is. How do we know that? We go to the assemble tab, and then we look up the label definition of main, which is here, and we can see the next location is indeed at location 10 in hexadecimal. Okay, so there is a strong relationship between the analysis tab and the assemble tab. Most of the correlation is already established by the spreadsheet itself, but if you want to double check and make sure that, oh, how do we know that address 10 is in fact the label definition of main, you can do that. You can actually just double check it. I suppose I can um, make the spreadsheet even recognize label definitions. So whenever a location corresponds to a certain label definition, it will spell out and go like, hey, this location is also known by this particular label. Suppose I can do that. Note to self, okay, another enhancement to be made to this tool. Anyway, but we don't actually need that, okay, because we can always just kind of switch between the analysis tab and the assemble tab. The next instruction is a decrement D, because, oh, wait, the next instruction is LDIA6. So A has a value of 6 now, to be expected. Decrement D, D becomes FF, STDA. Okay, this is important, okay? Because now we have evidence that we are overwriting the last location of RAM, which is location FF, with a content of 06. We just pushed 06 as a value on the stack. Is that okay? All right. So this is the assembler that I think all of you can see. Yeah, this is the assembler that you can all see. So you are more than welcome to make a copy of this, and then you can start to kind of annotate things using all the additional columns if you want to. But this is how we push 6, and then the next few instructions would push the 2, and then the next few instructions would push 1E, which is our return address. Is that okay? All right. Okay, so this is important, okay, because by this time, okay, it doesn't show it like this in the trace, but if I were to try to understand all this stuff here, I would draw myself a picture, okay, in other words, I would draw myself a snapshot at this point, and I forgot to take my tablet with me. Okay, but that's okay. I can just use I can use a text editor, like a regular text editor to do this. So let me go to my mouse pad and kind of specify what I meant by that. Okay, so on the side, it might be helpful for some people to kind of go like, okay, location FF is now a 06, location FE is now a 02, location FD is now a 1E, and the stack pointer is pointing to that very last item that I just pushed on the stack. This is important because these 3 bytes are need to be used by some as a callee. Okay, so that means by the time I get to the callee, which is very soon because I have a JMPI here and then it halts. But this halt instruction belongs to the callee, which means in the original code, this is where we are at this point, at this halt instruction. What is on the stack? The stack has 3 items on it. We have one, I cannot remember. My short-term memory is actually very, very bad. So we have 1E as at the lowest location, 02 at the next location, 06 at the last location. And I'm just going to use an extra parentheses. I'm not sure I should do that. Um, I can say D points to this location to indicate that is where the stack pointer is pointing to. Okay, but these are just the values. Exactly what do these particular values mean is the next thing that I need to kind of differentiate. So now I'm going to comment this out, and then I'll say D is pointing to the return address. The next location is the first argument, which is X, and then the next location is Y, which is my second parameter. So from the perspective of the function being called, um, the 02 is known as X as a parameter. The 06 is known as parameter Y. The return address has no particular name in C++ because in C++ we simply do not need to know where the return address is. But in assembly language programming, we do need to know that. Okay, I'm going to pause here and see if there are any questions. Are we good so far? Yes? Okay, all right. So what do we need to do in sum? This is the C code. So I'm going to comment here just to repeat what we need to do is to compute X plus Y. All right. How do we get to X and how do we get to Y? Hmm. Most people would go like, oh, we can increment D so that D would point to X. So this is another thing that I probably need to add to the caller-calling agreement is you don't want to change the stack pointer up. You don't want to increment the stack pointer unless what the stack pointer is pointing to is no longer useful to you. Okay? So I will do it right now because if I don't, I am going to forget. So the caller-callee agreement, oh, this is using the old way of documenting. So let me do some changes here first. I changed the way I distribute the module several times in the past year or so. So this is um, the current way using GitHub. I've already done it in GitHub, so it should go to the GitHub page. Or not. I forgot. I haven't done it yet. Okay, so I have to make a note to self that I have to do that next. All right. So let me just kind of visually describe what I mean by this. So you have a stack. Okay, the stack starts from the top, and then the stack pointer points to a certain point, somewhere in red. Okay. So what you can do, since today is Halloween, we'll just kind of imagine gremlins. Okay. So this is your code. Okay, this is location 00. This is location FF. So your code starts from here and it fill up a certain kind of space in your program. This is your code. In other words, the assembler will assemble content to fill up the program or fill up the RAM space from 0, 0 up to a certain point. Is that okay? And then this space here, okay, which is the byte below where the stack pointer points to, and above the last byte that you utilize in your actual program, that place is open to gremlins. They can appear anytime and just come into this space and make some changes to this space without letting you know. So I'm not going to tell you what those gremlins are in terms of actual technical term and why that can happen, but it just happens. Okay, in an actual computer, that is what will happen. Okay, so that means the moment you change your stack pointer, you move it up. Okay, the moment you move your stack pointer to the next location, this location can be modified by the gremlins, and you have no control over when and how the gremlin is going to change that location. You will not be notified. There's no way you can tell. So what does that mean? Well, that means one thing. You don't change your stack pointer to point up to point to the next location unless you are sure this location is no longer needed. Is that okay? So let me say that one more time, okay? Decrementing the stack pointer is not a problem because you're just moving the fence to have more space that the gremlins cannot touch. Is that okay? So decrementing the stack pointer is not an issue. But incrementing the stack pointer means you're moving the fence closer to yourself as to where the gremlins can modify, can mess around. Okay? So you have to think first. It's like um, the area where the fence is going to be moved over. Do I still need that stuff? If you are really sure that you don't need that stuff anymore, sure, move the fence closer to you and expose more to what the gremlins can modify. Okay? Is that analogy working out okay? All right. So if you're super curious and go like, okay, I want to know why that is the case, the concept has to do with interrupts. But we are not going to talk about interrupts yet, okay, because we have to finish talking about functions first. Okay, so getting back to our example here. So we cannot do this, okay? Incrementing D is not a good idea. Okay, so what should I do? Well, maybe we can do something like this. LD register A with register D plus 1, okay? That won't work. Why do you think this is not going to work?
D plus 1 is not a register.
Exactly. So D plus 1 as an expression does not specify a register. Okay? We can only specify a register with the LD instruction. And why is that? There are two reasons. Okay? From the syntax perspective, when you look at the LD instruction, it says Y has to be a register. Okay? But that's just a syntactic rule. Okay? Okay, forget about syntactic rules. I can just go straight to the opcode. The opcode does not let you specify YY is not just register D, but is one added to register D. In other words, from the opcode perspective, there's just no way to specify I need whatever 1 plus register D has to specify the where I need to be referenced. It cannot do that. But if that is not enough reason to convince you that this is not something that we can do, I have another explanation, which is the most relevant explanation up to this point. Okay, so let me start Logisim and then load the processor. Okay. This is the reason why I use this architecture, because you can actually see it. Tell me a way to add 1 to what register D has and then use it to route register D plus 1 to the A port. Okay? There's no way to do it. There's simply no pathway to make that happen. Not in this processor. Does it happen? Can other processors do this? Some, yes, can do this, but those are not RISC processors anymore. They're CISC processors. In other words, they trade more silicon to make instructions more compact. Okay, but by doing so, they also increase the amount of energy that it needs to get the same thing done. Okay, it is counterintuitive because most people would think, hey, with a RISC architecture, if you need to execute more instructions to get one thing done, isn't it going to be more? Isn't that going to be less energy efficient compared to an architecture where you can specify fewer instructions to get the same amount of work done? Well, as it turns out, it doesn't work that way. Okay, because by complicating the hardware or the silicon part of a processor, you need more silicon, and more silicon just translates to more power consumption, and the equation favors architectures that have simpler instructions and fewer transistors in the core, in the processor core. That makes it actually more energy efficient. Are we good so far? Okay. So there's simply no pathway in the processor to do what I just tried to specify in the assembly code. Then you go like, okay. So what do we do then? Okay. Yeah, you can always just kind of do a CPR CD. Okay, so this means C equals to D. This is just a copy register. So that means at this point, okay, if I were to comment, what the registers look like, is now we have both register C and register D pointing to the return address. Is that okay? Register D is already pointing to the return address, which I don't want to lose. Okay, I don't want the gremlin to override that location, so I cannot move register D. But by making a CPRCD, basically copying register D to register C, now I have register C and register D pointing to the return address. Is that okay? We good so far? All right. So now I can say, I can now increment register C. So what is that going to do? Oh, I said register C. So what that's going to do is to say, okay, register D, you stay put. Keep those gremlins from modifying the return address and everything beyond that point. But register C, why don't you point to the first argument X? Is that okay? So register C is not parameter X. It is the address of parameter X. Okay? So that means if I were to comment this, I would say C is now D plus 1, which is known as the address of parameter X. Okay? So once I get to parameter X, I can go like, wait, I need whatever parameter X is, not just the address of. Yes?
So the address of parameter X is a value, or is it just an address?
If you're referring to the address of X, it is the address of. If you're referring to just X without the address of, it is the value of.
Yeah, but you're incrementing by one. So how can you increment an address?
Well, if I had the address of the return address, incrementing that address by 1 will get me to the address of X. I'll show you when this code executes. We'll get to see. Okay, so let's actually execute the code right now, without finishing the program. This is actually what I would also recommend you guys to do when it is your turn to write your code. Okay, you're going to be writing your code in about, I would say, but maybe a week or so. Then you will have all the tools that you need to actually start to write your code. But this is also something that I want you guys to use, is to say, I'm not going to finish the entire function first. I'm going to break it up into smaller chunks of code and make sure that at each chunk of code, I know what I have on the stack and in the registers, and everything is consistent with my understanding of what the code is supposed to do, which is exactly what I'm trying to illustrate here. So I would have to remember to save this code and then go through, just run it again. So this is why I think, if you have not yet set up River Spider, you should do it, because this is how you can make some modification, small changes to the code, run it again, and then go to the trace and see, oh, okay, what is happening here? What's happening to the stack pointer? What's happening to register C, register D, and so on. So now we can go back to the analysis tab. Okay, this is where we left off last time. So last time, I had a halt instruction at location 0f. So this time I go like, okay, let's go ahead and copy register D to register C. So the end result is now register D and register C are both FD. What is FD? It's the address of the last thing that I pushed on the stack, which is the return address. So this is the address of the return address. But by incrementing register C, it is now register C now has a value of FE. But what is FE? Well, FE is 254, but it is also the location where 02 is, and 02 is parameter X from the perspective of the callee. It is also known as the first argument from the perspective of the caller. Okay, so I'm going to pause here to see whether this is all kind of making connections or not. Yep.
The FE said is pointing towards 02, right?
FE is the address of the 02 because this tells me that I stored 02 to location FE.
Yeah. So, did you say the value of FE was 02, or what is the value?
The content pointed to, okay, the value of location FE is 02.
How does that relate to you said it's in the first parameter of the function, right?
02 is the first argument from the caller's perspective. From the callee's perspective, it is parameter X, which is the first parameter. This has to do with how we push the arguments in a reverse order. The last argument was pushed first. So the first parameter has the lowest address. And then the very last thing we pushed was the return address. So that means you have all the arguments pushed in this direction, and then after the first argument was pushed, then we push the return address. So the stack pointer would be pointing to the return address, but right after the return address, we will find the first argument. So that's why a picture helps, okay? And that is also why I am including a picture of sorts in the actual text file. Is that okay so far? Okay, so this is the part of this class that really requires a good understanding of pointers in your previous class in CISP 360. Okay, so if you're thinking, okay, my understanding of pointers is a little bit shaky or not, what I think it should be at, then you probably need to find some resources to help you clarify the concept of pointers. The best way to understand pointers and most concepts is to design small programs, okay, as small as it possibly can be, and use a debugger to go through those programs to double check whether your concept is correct or not, your understanding of the concept is right or not. So I do want to finish this program. So now that C is the address of X and I need to add the value of X to something, how do I get to the value of X instead of just the address of X? Which instruction should I use? LD, very good. So I would use LDAC. So that would make register A the dereference of register C, which is the dereference of the address of X, which is, okay, that just boils down to X. Okay, let me put extra parentheses so that we understand what we are talking about here. Okay, so the reason why I can say something like this is because after the increment C instruction, register C has the address of parameter X. So when I dereference register C, I am dereferencing the address of X. Dereference and address of, they quote unquote cancel out each other. So whenever you see asterisk and then this together, they kind of cancel out. Because one is taking the address of, the other one is saying, what is at that location? So they kind of cancels out. So that means we cancel out these two and we only have the value of X left here. So by the time we get to the LDAC instruction, we should have the value of parameter X, which is 2, loaded into register A. Okay, so if you are not sure about whether your understanding of this is correct or not, then what you do, which is what I would also highly recommend, is to run the code right now. Okay, with the very last halt instruction still in place, so that we are not proceeding to do anything else at this point. So now we go back to the analysis tab, and we go like, did we end up with a 2 in register A? Yes, we did. So this trace gives you everything that you need to understand what is happening when a program executes, but it doesn't give you an overall map of what is where in memory. So that is something that you kind of have to track on a separate piece of paper, on a separate spreadsheet, and whatnot. In the code here, I am attempting to accomplish that thing by using this notation here. The square brackets is representing what is on the stack. Whatever D is pointing to is the top of the stack. Is that okay? All right. Well, we also need to access Y because after all, we need to calculate the sum between X and Y. So that means, hey, if I increment C again, what is going to happen? So we'll take a look at the effect of incrementing C, not D, okay? So that means, okay, let me take that back because I need to copy from this one. So this is where register was pointing to, but since I'm incrementing C, now C is pointing to Y, or the second parameter. Is that okay? Okay. So that means the effect of this particular line is C is now D plus 2, which is now the address of Y. So once again, how do we know this for sure? Save the code, run it again. So you guys really have the benefit of having tools that can run, basically illustrate the result of running a program, somewhat interactively. Because back in my days of computer science, you turn in the code, and then you have to wait until the code is scheduled to run, and then all you can get is a printout of the output of your program. So your debug time cycle is extremely long. Go ahead. Sorry.
No, I'm just like, that's crazy.
Oh, but it's already a big enhancement compared to punch card days. Because with punch cards, you submit a job and you have to write your program in punch cards. So you have to, for every character in your program, it corresponds to one line on the punch card. To specify JMPI, it would take 4 lines. You have to punch out the JMPI. You have to punch out those particular lines on the punch card. Yeah, so I already started off with a dumb terminal, which means I can actually type things in without having to use punch cards. So I consider myself pretty lucky already. But you just don't get a feedback right away. The feedback is only coming back as a printout. You don't do anything interactive like this at all. But what that really, oh, okay, so the program is now going into La La Land, okay, because it's not doing what it's supposed to. I screwed up something. The gremlin. Halloween. I think that I might have made some changes to the spreadsheet here. It says you cannot find the value 02 in VLOOKUP. Alrighty, what did I screw up here? Okay, I think I screwed up the assembler itself. Okay, so when this happens to you, you can type Shift Control Alt H, and then it will give you this option here. And what you can do is to kind of go back to an earlier time when the assembler was still working, and then just say, restore this version. So this way, if you accidentally made some changes that kind of screwed up the assembler, you can at least get it back to a certain state. let's see. Sometimes it needs a refresh of the page to get everything to display correctly. Okay, so it looks good here, and we'll try again on the command line. All right. Yep. No, the app script is not affected by the history. So now we got everything done correctly. Okay, very good. So the question now is, did I correctly make register C point to the second argument when I called sum? The answer is, well, let's see. It is now at FF. But what is the content of FF? This is the one part the assembler, I mean, the trace does not give you like straight right away. So you kind of have to go back and go like, oh, last time I changed location FF was to change it to 06. So 06 is the content of location FF. And what is the context of 06 in this particular program? Oh, that was the second argument when we called sum. The second argument of sum is also known as parameter y from the perspective of the callee. So that means, okay, so everything is still kind of doing what they're supposed to be doing. So I need another LD instruction, but to a different register. So this time, B is going to be the dereference of register C again, which is the dereference of the address of Y, which will give you the value of Y. And then at this point, I can perform the actual add instruction. I can add AB, which means register A is now just X plus Y, because it had the value of X to begin with, and the register B has the value of Y. So when I add those two, I actually get the sum of X and Y as the parameters. And so as a result, I can now return the code. Okay, at this point, I can just go ahead and return, and which is LD, BD. This is popping the return address. Okay, increment D, JMPB to continue execution to the caller. So that finishes the entire program, which means this halt instruction can now go away. So let's go ahead and take a look at the quote-unquote finished product. Because we are, okay, so before we go back to the analysis tab, one thing that you need to do when you're going through this kind of exercise is to know ahead of time what you are expecting. Okay, so the way that I finished the program is I finished the call, okay, I finished the implementation of sum. So that means the sum of 5 and 7, which is 12, should be stored in register A, and I also finished the return code back to the caller. So that means I really should be at the halt instruction of main with register A being 12, which is 0C in hexadecimal. Is that okay?
Are we adding 2 and 6?
Hmm? Oh, 2 and 6 is 8. Sorry. Yeah. I forgot. We were adding 2 and 6. Okay. So now we go back here and then we scroll down and the last time we update register A is right here. It did end up with a value of 8. And we did go back to the halt instruction of main because line 26 is location 26 is the halt instruction that is in main. So in the past 80 minutes or so, I have illustrated, how to work with the return value and also how to work with parameters. And those two, both of those, fall into basically the agreement between the caller and the callee. I do need to go back and fix the reference because I screwed that up because I thought I'd changed it to GitHub already, but I have not done so. So in order for you guys to be able to read it, I have to change that reference back to where it was. So let me change that back, which is here. So that would be DTKB, Dr. Tech Knowledge Base. And then my account name, teachers. There we go. Date. And I'm gonna double check to make sure it works. You gotta be kidding me. I thought I changed that. I changed the wrong one? Ah, classic. Alright, sorry about that. Caller, call the agreement. We'll change this one. Alright, we'll refresh. Canvas doesn't know that I have just changed something. So even though it looks like, it should have worked, it does not do that. Typo. You guys are looking at ADHD in action right here. So what do I do with ADHD? I just know that I have to double check things, like a lot. All right, so double check one more time, refresh, and then go back and make sure that link works. But what you need to know is actually in today's lab as well. So today's lab actually contains the instruction to teach you basically the same thing. So you get a double exposure just for today to the content that I was talking about. So I'm not trying to teach you all this material just once, but it's also actually in the lab itself. All right, so I'm not gonna bore you with all these testing. So we'll go to the lab today, which is this one, calling and nope, not this one.
It's down at the bottom.
No, at the bottom. Parameter and return value. So I will move this up to here so it's easy to find it. And the passcode is frame. Lowercase frame. There we go. So I do have a hard stop today. By 11:50, I do have to get out of the classroom because I have interviews again today, starting at noontime. So I'm gonna have some fun time in the afternoon. All right, so you guys can go ahead and get started with this one, and I will do my thing to update the caller callee agreement. It's the same thing, kind of similar. All right, turn up the screen. Hmm?
I know I'm supposed to be looking at this. You have to follow the code, right?
Hmm.
Um, this just means that D is pointing to.
It means D has 0. That's all it means. D is 0.
Because this is the program counter plus plus, which means program counter plus one, right?
Yeah, but the effect of this statement is the same as loading whatever I is into register X.
Load I into register
Yeah,
X,
like the
which is
second.
zero.
Yeah,
Zero.
yep. In this case, it is 0.
So that means that register D is zero.
Yep.
Register A, you're returning.
It's whatever the label return L1 is. Return L1 is defined down here.
Oh,
Yeah.
okay.
Yep.
Thanks.
Label definitions.
saves the value of register D.
Yeah.
And then
Yeah, that's become far away from reach. I mean,
which is why it's
obviously,
confusing.
the stack.
Question 4 is trying to use that as a parameter to tell X, Y, Z. The first part of the part is called program.
I thought D was always a stack.
It is.
Should be.
It is, but except for setting the values in D.
Which is,
It
I
doesn't
think
really
everything
straight
goes
up.
faster though. Other than hour and a half. And that's where everything goes to, to D. All day.
I mean, yeah, but I mean, it was like copy over D, take it away, push back over D. It's like, oh man, I'm still, here's an independent
Yeah.
variable, not in programming terms, like independent variable, but like actual life terms, independent variable. You go ahead and do it.
Low to 0, low value. It's fine. B to D. D.
I'm on the website right now, but I pretty much looked at all the arguments. So what is 5 and 6 are fairly similar. The difference is D, which is should be kind of 1. Since you don't know what D is, you should start at 0.
Yeah, you usually start at 0. But when it says decrement, the ST is usually still on positive. After the value is saved in the register. And then we
That's what I'm saying. So
well, I don't think register D is actually B. Register A is.
So,
Flashback back.
so within
Number two,
when you're
I'm
storing
still a little bit
A,
confused
so
by
it's
the
B3, B4,
position,
B5,
the logic specifier identifier.
B5.
So I just remember that basically
We don't.
when you're
We
pushing
never
in
actually
something,
decrement.
how do I
Yes.
explain it?
So first thing is you push all the arguments, last argument first, and then you push the return address.
And that's where I got
Oh, it's still
confused. So in
return
this
values.
code here, for example, are you pushing it from up here, like, and then push it down? No.
Yes,
Okay.
because SP minus minus is a part of push, right?
Right.
So that means that whenever we push, we are decrementing the stack pointer.
Okay. So
Are you on 1? Yeah, exactly.
where is argument 5 compared to what D points to? What is argument 5? Is that this?
The argument that has a value of 5.
Oh. Okay.
Oh,
There's only one argument, but the value of that argument is 5.
And
It
that's
says
what I
def D,
was confused
ST.
in the lecture as well. So would that mean the return address would be at F, and then the argument
If
probably
that's the
below
first thing
it?
we do in the program, then yes, the return address would not be FF because we push the argument first.
So the argument would be FF.
The argument will be at location FF, and the return address will be X by down.
Okay.
But it doesn't even matter, where the stack pointer was. The question is asking what is the relative distance between those two.
I'm pretty sure, yeah.
1 byte.
1 byte.
Yes.
So
No, you're fine.
So
Go
when
ahead.
you push,
I'm still on.
it's gonna basically take whatever addresses here and bring that down.
Okay, so let's re-examine the sequence of what push is, right? So push says minus minus SPP, and then whatever SP points to gets whatever value that you want to push.
D. So we're gonna
Okay.
we're gonna push D
So
from the
that
value of
means
A because now
if the
XD
stack
is going
was
to the
like
address
this already,
wherever the address
whatever
is,
this
will
turns
be
out
with
to
the
be,
value of A.
the first thing you do is you say,
We jump to
okay,
5,
you're going
which
to
is
point
where A
here.
is gonna be.
Then
We'll
you
enable 5.
overwrite this
A
location
is
with
or
X.
D is the pretty much the initialized variable.
Yeah, we
That's
initialize
zero.
from 0.
Okay. And then
Yeah.
Mhm.
And then after that, yeah,
okay.
we're pretty much
And then if you want to push
copying
another value,
A.
you just
So
go
you do
down
the same
again.
thing. Yep, you repeat the whole process, right? So you say, okay, move this down here,
A should actually
and
be
then
the parameter.
put whatever you're supposed to put here.
When you go
And then
downwards,
function
does that go
5
to a higher
loading A
number?
with value 5.
Because
We are
what I was confused about is
loading
this starts from
register
the
B
top,
with whatever
Yes.
that's
which is
in
the
the address.
last
Okay,
row.
high address. It
Uh-huh.
starts at a high address. At the top of the stack
Now A
is
is
always
5,
what the
which
stack
we're
pointer
loading
points
E
to.
with A. You know what I'm saying?
That's
So
called
Yeah.
5
the
goes from
top
A
of the
and
stack.
also
It's
D.
whatever the
Yeah.
stack
And
pointer
then
points to.
readers too.
And
You
then we are
referencing that shit.
Yep, and then now we're incrementing the
Okay.
E, which is
Mhm.
I guess we have stack pointer, and then so on to the next location, and then we're jumping should jump to B, which is where the B is supposed to be at, which is D. It's kind of confusing.
I'm trying to explain it to
Yeah,
me.
I don't understand myself either. But
Speak English.
I know, right?
A has the value 2,
Where
then
is
you
the
add
variable?
to the address known address. So it goes up to the stack actual location. Okay, so yeah. That's the value. It's the address.
Oh, go ahead.
Would you be willing to help me figure out why my reverse picture's not working? So I just ran it with the test,
Mm-hmm.
and then
Okay, you have a timeout. Okay,
Oh, I have
so
a timeout.
let's go back to here.
okay,
G timeout is a command that is not found. You can just delete that command. Yeah.
Oh, that's right. I was trying to figure that
Yeah,
out.
because
Okay.
on the Mac the command is different.
Yeah.
In Linux it's just timeout itself,
Okay.
which basically gives a certain command a fixed amount of time to run. In case your program runs away, it has an infinite loop or something, it would just give it like 5 seconds to do
Okay.
whatever it can.
I remember reading about it in the README, and I tried to download it, and it wasn't really working. So
Oh, okay. You
and I
can
forgot all
just
about it,
remove your G timeout. It won't change anything, but if you have an infinite loop, then there's nothing to catch it.
Okay. Got it.
Yeah.
So for the number 2 right here, I know you're loading the register A with
they're valued at 5.
Hmm.
And then you're decrementing, since we're talking about functions, you're popping the stack on.
Nope. This is pushing. It's not.
Oh, decrementing is push, and then store D isn't push.
No. Push consists of two. These two correspond to push. So
Decrementing, and
you
then
need a decrement and a store.
and the store is
They're
corresponding to
both
the
part
same.
of push.
So they're part of it, but not the same thing.
Say again?
Like they're part of it, but not the same thing.
They're not the same thing, but they are both needed when you're pushing something.
When you're pushing. So, for instance, if I'm decrementing D, I'm pushing um,
It is a
the
part.
register D
No, you're not pushing register D. You're pushing whatever you are storing.
into D.
Yes, whatever you store into where D points to, that
Yeah.
is what you're pushing.
So D is going to be an address initially, since it doesn't.
D is always an address. That's why it's called a stack pointer.
Yeah. So basically, then I'm pushing the address of D in my stack.
You're not pushing D on your stack. D is your stack pointer. You are decrementing the stack pointer, which is register D, and then whatever you want to push, you store that to whatever the stack pointer is pointing to.
Gotcha. So like visually, this is the pointer, and then when I'm decrementing it, that means I'm moving it from somewhere, and then
Below, you're moving it one byte below where it used to be,
get one byte below where it used to be,
yeah,
and
and then you store to that location.
store it to that location. And this just means that I'm storing that pointer. I'm moving it to whatever that value or address of whatever that location is.
We are storing to whatever the stack pointer is pointing to.
Yeah, and that'll be like an address since the X. When you have a value of X, that just literally means just the address, right? And this
X is not address. SP stores an address of where we want to store X.
SP stores and that. Well, yeah, because this is the pointer. So this.
Okay, what is a pointer? There are three things I can think of that you're referring to. You have to clarify which one.
So my idea of a pointer is that the pointer is an object with the value, name, and the address into it.
No, a pointer contains an address.
Or
A pointer is the value of a pointer is an address, or should
yeah,
be used as an address.
yeah, but like in C++, there's you can change the address of a pointer and change where the pointer points to, and you can assign the value of a pointer to just a regular value like 5.
Yes.
So that's why I think of it as an object with 3 different parameters inside of it to make it easier to understand.
No, that would not be the way I would describe it.
So what would be like the way to describe it then? It's just an address that you can point to different things with.
Okay, the value of a pointer should be used as an address.
Yeah.
And what you can do with an address is you can dereference it. You can also, add or subtract from an address. You can perform address arithmetic or pointer arithmetic. So those are the things that you can do with an address.
Yeah. Okay, so I get that part. I'm just stuck on like I know when we're decrementing the pointer, it goes down 1 to wherever that it's gonna point wherever that is. I don't know what that is until I'm given some information, right?
Okay.
Because initially the stack is gonna be empty, right?
Well, we don't even need to know whether the stack is empty or not.
Yeah.
We don't need to know that. So if we assume that D is already, let's say it is already at F5, okay, for whatever reason, okay? The first thing to do is decrement D, which means D would now be F4. F4. And then when you do ST, A, whatever A has, now it depends on what A has, right? So let's say A has one E, as in hexadecimal. So what this would do is it's going to change location F4 to 1E.
That makes sense. Yeah.
And this is push. This together is pushing 1E on the stack.
Yeah, and that D equals F4 is what it's pointing to, right? You already decremented it, so it moved to where F4 is. That's what it
It
is.
started out as F5, but
Yeah.
after this sequence of instructions, then it becomes F4. After this, it becomes F4.
And you're
After
giving
this, the content at F4
is 1E.
becomes 1E.
So you wouldn't say the value of F4 is 1E, you would just say the content
I would say the content at location F4
is
is
1E.
1E.
But isn't it the same as just saying the value of F4 is 1E?
If you prefer to say it that way, you're free to do so,
Yeah.
but I would not.
Okay.
I
But
would
it's still
always say that the content at location F4 is 1E.
okay.
That is, I'm sticking to that one.
Okay. The content of at location of F4 is 1E.
Yes,
Okay.
because that is, to me, that is the most clear way to distinguish which one is the address and what is the value, what is the content at the address.
Okay.
Yep.
I guess it's
It's
just
kind
all,
of like, who lives at this house, right?
yeah, that's why I described it as an object with different parameters in it.
There's no object here
Well,
because
that's just
because
how
in regular C there's no concept of an object.
yeah.
So that's why any reference to the concept of an object is implying certain things that does not is not even here in regular C programming.
Yeah.
Yeah, because object implies that you're dealing with a class, you're dealing with an instance of a class, and we are not dealing with actual object-oriented programming here. So there's no actual object.
Okay. So when you say decrement D and it's stored D with A, then that means that if A is 5, then you're storing the content of D with 5.
You're storing to the location pointed to by register D.
With 5.
Yes.
With the content of 5. That
You're
makes sense.
overwriting that content with 5.
Okay.
Yep.
That makes sense.
Because I have a question.
Yep.
Why are we storing return address first, not the last, if you're using last? Because we call the function, we use the parameters,
Mm-hmm.
and after all, we need the return address. Why
Mm-hmm.
not store return address last?
Because in C you can pass a variable number of arguments.
Okay, but it doesn't change.
Well, then it becomes impossible to find the return address if you don't know how many arguments are actually pushed on the stack.
How do you pass indefinite amount of arguments?
You can define the C function like void. You have to give it one argument first. So let's say input, then you can use the dot 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 notation or whatever. So in a caller in main, you can now call f with 23, and then you can pass any number of things after that. So because this can be any number, so that means you don't know ahead of time the number or how many bytes are going to be used for the arguments. And as a result, if you push the return address first, then you will not be able to find it because you don't know how many bytes to skip to get to the return address.
But we don't have to skip it. We have to use the.
But you don't know where it is. That's the problem. Because if it's the first thing that you push and you push a variable number of arguments, then the stack pointer points to the very last argument that you push on the stack. But in order to find the return address, you have to know how many bytes were actually used for the arguments. And because you don't know how many bytes you have used as the arguments, you cannot find the return address anymore. But if you do it the opposite way, then you can always find the return address. You can always find the first argument. Okay, now the first argument usually would imply how many more arguments you have on the stack. So you can use that as a clue as to, okay, what do I do with the rest of the stack? Yep.
For this one, I thought it was 5. I was wrong. So what value should we fill in to make this TTP assembly code work? So
It is not 5 because you're looking at it from the perspective of the call B. So whatever you add the stack pointer to A should become the address the of the parameters.
Okay. Because you gave us this code up here, so
Yeah.
we pushed in 5, then we pushed in the return, and then we went into
5
the
is the value that got pushed on the stack.
Uh-huh.
But the
Right.
subroutine does not know what you push. It just knows where it is supposed to find 5. So the question is, how do I calculate where I'm supposed to find 5?
It should be at D.
No, because we pushed the return address last.
Right. So we could decrement. Wait, no, not decrement. Well, if we decrement.
It's best to draw a picture of what is on the stack. Because the 5 got pushed first.
Yes, so we have 5, and then we
So
have
5 got pushed first, and then we have the return address.
Uh-huh.
And this is the last thing that we push. So D is pointing to.
Yes.
So now I'm asking, okay, if I do an LDI A with something and then add AD, what does this have to be in order for A to point here? That's what it's asking. So what do you think? It's algebra.
Add plus plus to the D.
No, 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 no. I'm asking what should this be? It cannot be plus plus, right? That is just a single value.
Yeah.
So solve that equation.
Well, I thought it was 5.
No, it is not 5.
Address is going to be the value of that address divided by STD area. So FF is now equal to that 5.
Okay, I want A to end up pointing here. So whatever this is high location, this is low location, right? So this is where the low locations are, this is where the high locations are. We know that 05 is here, we know the return address here, we know D is pointing to this location. We want A to end up pointing to this location. And I need to know what I need to this thing here to be in order for A to end up pointing here after these two instructions.
Because if we made.
Okay, whatever you put here, we'll call this unknown K. Okay? So this means your A equals to K. This means A equals to K plus D. Right? We want K plus D to be here. What should K be?
Has to be right?
What?
I don't get it because we wanted to be 5, right? So
What?
this
No, no, no. It has a value of 5.
uh,
The address is D plus 1. This is where D points to. This is where D plus 1 points to.
uh-huh. So right, D plus plus is what I said earlier. Like I said, we can't do
No,
that.
no. We want to know what K is. Forget about plus plus. We are not dealing with plus plus here. I need to know what K is in order for A to be D plus 1. This is where D points to. I need A to point to D plus 1.
1.
Yes.
Oh.
You have to think in a sequence of instructions. Collectively, what does the sequence of instructions do? That is what this question is trying to get to.
So was doing D plus plus, but
Huh?
it was basically doing D plus plus.
No, it is not, because we are not changing D. D plus plus is auto increment of D, and yet nothing happens to D. D is only read but not written to.
Was this basically trying to get to where you want to basically make a where you guys you want to use whatever is above it, because if you were to
It,
increment D, it would be
this would have been the
relevant.
same sequence, the same effect is CPR AD increment A. It would have done exactly the same thing.
Yeah, okay.
Yeah, number 4 is 1.
I gotta look what I don't know.
Mm-hmm.
It was for
Question is look at it.
what is register A right after the add instruction?
Okay.
String credentials. Yeah, there's a formula.
See all these things.
The address of
Right after the
Figure it out.
instruction.
that would not be correct because you have to once again you have to picture what is on the stack. How many arguments do we have this time? How many parameters do we have on the stack?
We pushed in 4 first, then pushed in
No, that has nothing to do with that. You can read just this portion to determine how many is this. No, this the C prototype. So we have three things on the stack. We have three parameters.
Yeah, and then
So where are those parameters
where are those parameters?
relative to where the stack pointer points to?
Uh,
So what is the
3,
argument
2,
again?
1. What is register A right after the add instruction?
Okay, but what is the agreement between the caller and the callee regarding parameters?
It's pushed in reverse order.
It is pushing reverse order. Very good. So picture that. Draw a picture of
Okay.
where parameters C, B, and A and the return address should be, and what the stack pointer should be pointing to.
But so if we push in reverse order, is it always gonna? So let's say register C or A, whatever the last parameter is that always gonna be stored in FF or?
No, because FF is true only if the initial state of the stack is empty. We don't know where the stack pointer is pointing to at the time when we push something. So all we can do is to say, relatively speaking, we know this is going to be here, this is going to be here, this is going to be here, and that last thing is where the stack pointer points to. So we can only rely on the relative positions of things that we push on the stack. The absolute location, which is the actual address, kind of depends on at which point did you push that. Did the stack already have a bunch of stuff, or was the stack empty?
So only if it's empty, the initial push will go to that
FF location, right? Correct. Yep. So everything that we do is relative to where the stack pointer points to.
So we're not really talking about where in the RAM it is. We're just talking about relative where register A, where bit register A and
Register D
and
mostly.
whatever, and there really can be either one before or one after because it's pushed in order, kind of.
Because you don't really care about the rest of the stack either.
Yeah.
Because you're only dealing with the most immediate function call. So that means whether you're like 6 functions called nested deep, doesn't matter because all you need to know is where do I find my stack?
Is the address B?
Hmm?
Because
Why is this a 2?
why is it?
Because the stack pointer points here. This is D plus 0. This is D plus 1.
No, this is the values.
Okay, those are the values. Okay, very good.
Okay, and then we're doing 2, which is this thing.
Yes.
So 1, 2. So
It would be register, parameter B, the address of?
yes.
I think so.
Yeah.
So with
If you can see why it is important to draw the picture.
D, we're not
Okay,
taking
but
register.
I was just confused because in lecture I saw this,
But
Yes.
so I was just confused.
it's already
They
it
did
knows
like
D
this,
with
but
0.
Yep, but they accomplish the same thing. That is kind of one of the things that I need to teach this class is there are many ways to do the same thing. I will teach you one thing, but then you have to recognize how another sequence can get the same thing done.
Okay. I have 2 more questions.
Yeah.
Okay. Question 1.
Mm-hmm.
I got the answer, but I was still confused how I got the answer. Because I went through the process, but I was also confused. So, what, from my understanding, is we first initialize the stack pointer at 0, which is the top when it starts.
It's the same as location 256,
Uh-huh.
but 256 becomes a 0.
And then we want A to be whatever the return address is, and then we push that, and then we go to 5. So now we have register A to be 5. We want B to be the return address, and then we increment D that from pocket.
I think we're just loading A with return address of
Then we
one,
go to
and I don't think we do anything yet.
return address,
Unless when we
which
get to
is
that
here,
point, we jump to
where you
that label.
push in
And I push
a
register A, which is the 5.
yes, and then you want A to be whatever the next address is, and you push that in.
Yep.
We go back to 5, where A is 5 again, and B is whatever A was.
Which was also 5.
5.
So now we have 5 added to 5,
Which
which
is
makes it 10.
whatever the address is of D.
And then one more thing for the opcode. Over the weekend, I'm gonna go over this and
D,
have more
and then
notes
wherever
on
the
it.
address is,
Which was the ones that we
you
didn't
store
cover?
the value of A.
JMP was the only one.
JMP was on
You mean
the-
relative to Tuesday? Like this
no,
Tuesday?
like the like
Which
our
value
next
is
I don't think I've ever seen
Another
That's right shift. So the RTO actually tells you what it does.
Yes. So for the exam, we just have to know all of them.
Okay, and then you go to
opcodes.
return address of
For the
label 2,
final exam,
which
yes.
loads
But for
register
the
B with
next exam, mostly
Address of
just
D.
what we have used.
whatever it is whatever the return address of D, and then you add it.
So basically, all of those.
Well, it's open book, open notes.
No,
So
now we
once you
gotta
have
work
the
backwards.
once you have the opcode table in front of
What
you,
is that load
you
address
just have to
of
refer to the RTO to know what it usually does.
Because yeah.
And I'm trying to see how we got to that.
I'm right there with you.
Nothing. They
I'm,
keep
Oh,
going.
okay.
Yeah, I think before we, so when you add 1 to D, that points back to 5, correct? Because it's
It
on the stack.
points back to 5. That is correct.
How did like we figure out we needed that though exactly like from the code?
Because of this comment. This specifies the return value. Because register A stores the return value, then you ask what am I supposed to return? I'm supposed to return the value of the only parameter that I have, which means before the LD instruction, register A needs to have the address of the only parameter that we have. That's how we know that
Okay.
where it's supposed to be pointing to, and in order to calculate where it needs to be pointing to, we have to understand if I only have the address of the return address, where am I supposed to find the address of the first parameter? And you have to use the callie agreement and go like, oh, okay, wait, we push all the arguments first, and then we push the return address. So that means if there's only one argument, it will be right after the return address in memory space.
Yeah. Okay. Yeah, I was just wondering like, how did we know to do that? But that makes sense with the C code. It's like,
Yep.
to do the only one. Okay.
Yep.
So yeah, like that's what I got from the other questions too. That the parameters are like after the return address.
In terms of memory location.
Yeah.
Yes.
Thank you.
So number 3
Uh-huh.
on the left.
I have to see the question.
Okay. Because I cannot remember the question. I want to try to like draw it on the board for you, my understanding, so you can help me.
I need to know what the question is asking. Input of function, what does SP
The stack pointer, right?
The stack pointer does not point to itself.
All right, let me try to. Can I draw it out real quick?
Yes.
Okay. So my understanding, right, is that initially register A. So we decrement the counter after that.
We do not decrement the counter. We
Or
decrement
the pointer,
the stack pointer.
the stack pointer.
Yes.
Eventually, this is the pointer, right? moving down here. But I don't know what the value is here.
Well, then it depends on what we store at that location. So what did we store at that location?
Well, 5 is here, right?
Wait. Okay, wait. So how did 5 get there?
Because we loaded A into the register, or loaded 5 into register A.
Then 5 is an A. How did it end up on the stack?
Is the stack only storing addresses?
Well, the stack is just memory locations. Until you store something
Oh,
into
so
memory, it's not there.
It's nothing there right now. So when we increase it, the memory location
We did not increase we did not increase memory location.
decrease the stack pointer
We decreased the stack pointer, yes.
to, we went down, but what, like, I don't understand what's going on. Like, we decreased the pointer, but what exactly is supposed to be inside of here? Like, how do we know what it's pointing to?
You haven't stored yet. So it depends on what we store there.
Well, we stored A into
We
D.
stored A, but we didn't push it to the stack yet. I think that's what.
Yeah,
Right? We stored A in the register. We stored 5 in register A, but we didn't push it to the stack yet, right?
But we did push it to the stack on the third line.
Yeah, on
ST,
whatever
which
pointer
is
it's pointing
here.
to.
The ST instruction is the only one instruction that changes memory locations.
Yeah, so we changed it to 5 here, right? When we
That
had-
finishes the push 5
Yes. So this is correct.
after the store instruction, yes.
Yeah. And then we load A with the new location, rec 1 label.
Okay. What is it representing? What is the agreement between the caller and the callee? What the caller is supposed to push on the stack?
The caller is the function. The callee is whatever's inside the function that's getting called, I believe.
The caller is the code that is calling. The callee is the function being called.
Yeah.
So what is the obligation of the caller according to the caller-callee agreement?
That register A is supposed to only return scalar.
That's one of them, but that's done by the callee. So we are still setting up the stack right now. So what is the obligation when there are parameters?
You'd have to refresh me.
I don't need to. You can read it.
I just don't remember.
You can still read it. You have your laptop up. So
I still want to remember what I'm supposed to be looking at.
Okay, I'll try. Look, I'll try.
okay, so you go ahead and try, and then I'll come back to this.
So, look, so you're saying right. So, we are
That's why
passing A as an param, right? So it's why we are storing A in the stack.
Yeah.
Okay, then we are, wait, so what's
So that's what I was wondering, because
LVI
it
is,
asks
Yeah,
you
but
pass
this is the
the
whole
thing, so
yeah,
The augment
I want
function
to.
one by one. So
So-
after decrement, we stored the location 5
Yeah.
here, right?
yeah,
And then
at location D. we
This is
store
not gonna answer the
yeah,
question.
and then after that, we
Yeah.
stored we changed the location, like what it points to
Because
the
I can
new
get a
way,
general gist of
Yes.
where it's going to go.
So what?
If I
And
did opt for it, so I was just
do
wondering which ones we
whatever
don't need to do. So
depending
I don't
on
have to.
function definition.
Oh, I
right?
see.
And in main,
I mean,
you
they are
call
more
a function.
like they're fancy.
So you call a function just goes
These are all the
this,
same.
this does whatever it does, and it should come back here.
Yeah.
Once the function is finished, it should come back.
Oh, that makes sense.
So-
That makes more sense. 'Cause
Yeah.
it's just
That's what
telling
the
us
jump,
that we're moving here.
Yeah.
Focusing on
CSP
this.
is
Yeah, just come back here is return label 1.
Yeah.
In whose language?
So with each family, only
Yeah.
once you figure out one, the other one is.
But we're just literally just moving to that.
Yeah, we are just
Okay.
finished. So we are done,
Which is the stack.
and
And then
then,
if
And
you
then
refer to
after
it,
that,
how do we
we
know whether
decrement the
that's
count, the pointer again.
You don't-
yeah, we go to the next step.
Yes.
Yeah.
Because everything is relative to where the stack point
So
points
we
to.
want to continue
Right.
here.
And that's
let's
all
say
you
this
need to
is
rely
some-
on.
Oh, we
Where
moved
is
to a
the
whole
stack
new
point?
Because
stack.
earlier today you were like,
It's not a
okay,
stack.
so
So
stack
we
pointers
stack.
have FE, then other parameters.
Look at
That's just an
line
example.
numbers. Just do 1, 2,
Because you don't know when you don't know where the stack point is in
Yeah.
after our function
So you can
is
only
line
rely on
9.
offset.
So it
from
goes
where the
here, function is
Okay.
done.
So we don't
We have to
worry about
continue at line
location
10.
because that can
right?
always change.
So
That
10
depends
is
on
on
a
here.
lot of things.
Right.
So computer knows, okay, I should go to line 10.
Okay, yeah, so after we loaded immediately, we jump to this function, right?
No,
So,
just
because this is what this means, LDI, you load immediately register A with the location of the
yeah.
return label.
So A is location.
It's-
Let's say just 10.
Yeah,
for
it's
example.
register A.
Regular label.
After we decrement it again.
Yeah, we go to the next.
So now this is 10.
Yeah, this is a location where should we come back after function is
And then decrements again.
Oh.
Does it? No, it does not.
Yeah, decrements again afterwards. And then stores A, which is another 10. No, sorry.
Yeah.
This, we decrement.
Yeah, we don't go down. We jump.
Because I read it wrong.
The next is jump to the function.
Jump to XYZ.
Yeah, let's just say
It's some other function, we don't know where it's at, but it's just on that board.
yeah, it's going to the function.
And then now we're looking at the new label, and then we're incrementing D, which we're going back up.
No. So the function is completed.
Yeah.
Function did whatever it did. So because we stored A here, we here decremented it, right?
Gotcha.
It's here. We have to push it back. We don't need A as a parameter anymore. So we
On
can
the stack.
increment. Yeah, on the stack.
So this is why I'm stuck at. We jump back down to this function.
We have finished this function.
Yeah, we finished it, which is why what this is, right?
Yeah. So we are coming back to line, for example, 10 after function.
Location 10.
Location 10, which is here.
Yeah. We use
And
the
then we
Wait. Okay. So you have to be clear. Location 10 is not here. This is the stack. Location 10 will be somewhere down
Yeah,
here
it is.
in terms of the memory
after
space.
the function. Yeah.
So you're not continuing execution on the stack. You're continuing location of where this is pointing to, which is down here somewhere.
Gotcha.
But
So-
at that point, we still have 5 sitting on the stack. Why do you need 5 on the stack right now? Because you're done with calling that function already. You don't
So
want
each function has its own stack.
No. There's one stack. They make each function call makes use of a portion of the stack.
So pretty much the stack is a shared space. After you store something in there, if you don't need it anymore, go ahead and delete it from it. So it can free up room for
What does
other
that
functions.
look like though visually? Like I get the stack is one shared piece of data structure, right? But I'm just trying to follow it one by one so I can get the answer.
And that's what the trace is about. If you put that code into an actual program, then you can run it, and then the trace will show you, what the stack will look like. So which program are we talking about?
The assembler, right? Or
Which question are we trying to answer?
number 3, which is
Number 3. Oh, okay. Thank you. Ooh, I like the more pattern. This pattern is called the more pattern.
Which
It's the interference pattern.
Oh yeah.
Because it's not possible to show you what the stack looks like because it changes constantly. As we execute the code, the content on the stack changes. So you can only take a snapshot and go, this is what it looks like at this point of the execution of the program. And that's what the trace is trying to help you, is to show you, what the stack and what the registers have at any particular time in the execution of the program.
So it's saying the question is what is the stack pointer register or what is the stack pointer pointing to register D? Let me reread it. What does the stack pointer at register D pointing to?
Okay. So I'm replicating the whole code on the whiteboard. So we can do
Because
this.
if I can't see that visually, it doesn't. I don't know how you can even.
They have large cell open?
No, I don't have a lot of this open.
Okay. Here. Do you?
Yeah.
Could you
There's
open
like
the,
literally no way to get the answer without seeing
could you
it
open the
visually.
RAM? Yeah, edit contents. Yeah, here is your stack. Here is the stack. This is a stack.
Thank you.
It stores a program from the start, at the end it's stack we're using, we're going backwards, and it's storing values. That's our stack.
Okay, so I can teach you how to visualize.
Yeah.
Well, maybe. Everything is in the main. Okay, so it gets 5, nothing happens to the stack. So this is the stack. The stack point is already pointing to some location. We don't know where that location is, nor should we care. Okay? So now we decrement D, so we go like, okay, let's point over here. And then we store A to what the stack pointer points to, which is 5. So we have a 5 here. And then we change A to
The new.
return L1, return L1 which is here, okay, which is a return address.
Yeah, and that's just a whole new call for like a function of what this is.
This entire thing is one call. Everything from here to here is one call to the function called XYZ. That's one call. It's broken into tiny little pieces because each instruction can only do a little bit of work. Then we decrement D again. So we go like, okay, it's point here now. What should I store? I'm storing return L1 over here.
Gotcha.
All right. So at this point, this is where register D is pointing to.
Point to return L1,
Okay. And then we go JMPI to XYZ.
which is a whole new function, right?
XYZ is not even defined here. We just know that it's somewhere.
Yeah.
And I'm asking right here at this point, whatever the instruction is, I don't even care.
Yeah.
That's where the question is asking. So what did they ask?
Where's the stack pointer, quote unquote, register D points into?
So, okay, if we know it's pointing to this content here, the question is, what is the purpose of that byte on the stack? I mean, from what you described, what the question is asking.
It says
I believe
what? Oh yeah, what does?
because
Well,
we are returning the address of L1.
So, but what is the question actually?
it says what does the SP register D point to?
All right.
Which is
So
register
the
D
return
point to
address,
the
right?
return address, yeah.
yeah,
Okay.
that's what return L1 is here. It is a label defined right after the JMPI instruction. As per the caller calling agreement, that is where the subroutine, the function being called, is supposed to go back to. That's the return address.
Okay, that was all I was looking for. That's perfect. That makes sense.
But you can see how I did this, just based on the instruction. I did not know more than what you're supposed to know.
Yeah.
I'm just coming up with a visualization of this is what it looks like, which is also what I did in class with the traces. The traces show you the exact location, like this is location FD, this is location FD, and so on. But that's just an example of what if we started off with an empty stack to begin with. But the stack did not have to be empty. We can be halfway full by the time we get to this code. All it matters is what was the last thing that we pushed on the stack. That really boils down to what the question is asking. Is the return address.
Makes sense. Yeah, I got that.
Okay. But there are a lot of pieces, because the difficulty is to make connections between all the pieces. So this class does not just have breadth, it also has depth. So it's both the breadth and the depth that make this class more difficult than most other classes, even compared to calculus. Because calculus, I would say, has a lot of depth, but not necessarily a lot of breadth. It's the technique that is important. In other words, the knowledge that is learned here in this example, it is important by itself, but it is also how I come up with this visualization, going through the instructions one by one, and then show the diagram over here. That is also important. Yep.
So in regards to the code there, like for example in question one, it says LDID 0, right? So we're loading register D with the value 0, and when it says decrement D, we're not decrementing the value, we're decrementing the address. Is that correct?
No, we are decrementing D.
The value in
Okay, register D says I'm just zero
Yeah.
zero.
Yeah.
You can use me as an integer value, assigned or unsigned, or you can use me as an address. Until such time I dereference using register D, it is just a bit pattern. It's just eight zeros and ones stringed together. But until you use an LDE using parentheses around D, or you use an ST using parentheses around D, register D just says, I'm a bit pattern.
Okay. And then
That's
so
all it says. It's not signed, it is not unsigned, it's not an address. I'm just eight individual bits strung together. But as soon as you do an ST or an LD with parentheses around D, then it's like, oh, okay, let's remember how the pathways were done, how register D connects to port A of RAM. That is when register D takes on a really important role of specifying a location in RAM. We're using it as a pointer.
so when it says decrement D after restoring a register D with 0, we're decrementing 0.
We are just decrementing zero.
So is that still going to be 0?
We are literally doing.
Or is that going to be a negative? Negative 1.
Doesn't matter because the
Why?
next line is.
Why do you care? Okay. Once again, the question is why do you care? Because all we are doing is mechanically going through the binary subtraction thing. Okay. And we go like, okay, exclusive OR.
And it's still going to be 0 because the 0 flag is set.
And then we have missing one somewhere. Oh, right here. Okay, so this is the result, and this is what we put back into register D. But what is it representing? Is it representing -1? Is it representing 255?
Doesn't matter.
Doesn't matter. There's no context to give it a meaning yet.
Yeah.
But
I think that's what I was getting confused with.
But as soon as you have ST blah blah to register D where it points to, then it goes like, oh, whatever this bit pattern is, present it to the A port of RAM. And then suddenly it takes on a new meaning. It's like, oh, okay, I'm being used as an address to specify a location in RAM. So that is, I think the difficulty of understanding low-level programming like this is we automatically associate signed versus unsigned, pointers versus integers. We automatically try to assign those types to a particular bit pattern when there's none to begin with. It is until you use it, like in a compare, then you go like, oh wait, is it supposed to be signed or unsigned? Because right after a compare, you have to choose, am I using the L flag or am I using the C flag? If it is unsigned, you use the C flag. If it is signed, you use the L flag. So that's why it is a little difficult to transition from C to assembly, because in C the type is associated with the variable itself. So if we try to carry that, if we try to project that understanding to assembly language and go like every register has a type, that just takes you on a scenic route to nowhere.
So
because that is not the case.
So pretty much it just needs a value, regardless if it's 0 or whatever, just to get an address location. Is that what it's doing?
You mean register D?
Yeah, register D just needs a value of whatever that we're not going to use.
Register D is just an 8-bit value. That's
Yeah.
all it is.
Yeah.
Now, the way we use it from here on is to use it as the stack pointer.
Yeah.
So that's why it is special, because we use it as a stack pointer. But other than that, it is really just a register. Can we add to the stack pointer? Yes. Can you add the stack pointer to something else? Yes. Can you copy the stack pointer to another register? Yes. So it is just one of the four registers. It can you can use it for anything you want to as
We'll
the
consider
other
it
three
No,
registers.
F0, F1,
But the
F2,
role
F3,
is
F4.
playing here is the stack
Last
pointer.
one is gonna be
And the stack pointer is
FF,
important because of the
because
caller
16,
callee agreement.
16
That's what I'm trying to get.
is
We have to initialize it with zero
yeah, so
just to get
0,
a
0, 0,
location
1, 0, 2,
on the
0,
stack
F.
pointer, right?
Is
That's
that
why
Because
we're
we
this one is 1,
initialize
0,
the
1,
zero
1,
because the
1 F,
end of RAM
2,
is
1,
supposed to
whatever,
be the end
goes
of the
9,
stack.
A, B.
But the stack pointer is supposed to point
So
to
this
one
is
location
FF.
passive.
so we pointed. I mean, we
So this is
Or
location FF.
In 10
And when
bits,
you add
it's
1 to location FF, you get location 100. But because the stack pointer by any
I
other
don't
stack
remember like the
by any
binary
other
exit
register is only 8 bit wide,
so
it cannot represent
just
100.
house
It
number
can
is
only
256.
represent 0, 0.
The
That is why
person
it
who
is
is living inside is
initialized
2.
to 0, 0 because
House number
0,
is
0
255.
is 100,
Three is living in
which is location
house number is
256.
we only have
4 is living
255.
in so
That's
the
why we
question is asking.
decremented because we only have
I think so. The
255.
As
address
soon as
first
you
pattern is
decrement,
greater
the
than
interpretation of
address
11111111 is
First
255
parameter
or
goes
location
last.
255 in this case.
So it's 256, 254, or F3.
Question.
So it's less than because since the first parameter is before.
No, it's first parameter is greater than the
I'd
last.
like to figure out how I got 10
What has it?
without
Yeah, it's greater than just the last parameter. And that's because it comes first, right?
Yes.
I think I
That-
made
that's
I know I
makes sense.
realized I made the mistake
That makes a
of
lot more sense.
loading A to register 1, going immediately to register or to label 1 and going, alright, well label 1 is the decrementation of D.
What is the third right after that?
So long instead
What
of going
immediate?
straight down.
The register able to add a register D. Oh, we have to
We're
follow
working with
register.
register D, we'll load it with 0,
Define what's
right?
D.
And then, so it just has 0, it don't have no address. We can get register, it doesn't have the address yet, right? And we'll load register A with the return address of label 1. And then now we decrement.
We're pointing the location of D to
Now,
and
now we
zero.
push D
We don't care
onto the
about
stack and then we
We need the
decrement.
actual
Yes,
value.
you can do it
Yeah.
at least
So we know
So,
it's
yeah,
4 though.
D equals 0.
Because
So now we push D to the stack. Now
It's
it's actual
location
location.
D,
we
the
decrement.
value is 4, but they
A
don't know what's
is
D
return
equal to.
that's the actual address.
Oh yeah.
Decrement D, so
Decrement
at this
D.
point where D equals
Store D.
to
Again.
whatever, it was 0,
Oh, so
decrement.
we have a stat 4,
Yeah, so
3, 2, return label.
Yeah. 4, 3, 2.
I feel like we're pushing